everyone. No.
Because we've not really done any front.
Okay, hi everyone. We'll go ahead and get started in about a minute. I see some messages. Hello everyone, morning all. Hi everyone. From different parts of the world. So it's 8 a.m. in Australia. Thank you for those who are coming in from parts, of Europe where I understand it's really late for everyone. Okay, so we should probably go ahead and get started already because it's 8 a.m. I just make sure that everyone can hear me okay, right? I think it's fine. All right. So welcome to session 2. And today we will take a look at estimating secondary osteon density. If I could, can I please ask for you to mute your microphones? Is that all right? I can hear someone clicking. Let me just do this myself. I'm just okay. All right. Let's see if this is if it's letting me. It's kind of slow again. All right. So just like last week. Sorry. Okay. So just like last week, I would like you to please imagine that you're in the histology lab and you've got your thin section on the stage here at the microscope, and it's transmitting information onto the screen. And so last week we thought about how we could differentiate between young and adult bone. And so today we're going to think about possibly estimating what we call secondary osteon densities. Now, this is the image that you saw last week. And so I'm really only bringing it up again today so that you can have a think about how we differentiate between the different structures of bone histology and how we can use that in collecting data. And so for today, we will really only take a look at an individual osteon, or I should really say groups of them. So for today, just pay attention to what an osteon is, what it looks like, and I guess concentric lamellae as well, because they are an important part of, of what an osteon is. Now, also bear in mind that we're looking at just, some random region of interest in a bone. If you were to do this properly as part of your research project or anything else that, that you are doing, of course, please make sure that you collect your samples from, from a site that is relevant to your research question or to your hypothesis. And also please ensure that you sample bones consistently. So if you're looking at the midshaft, you've got several femora in one assemblage, you obviously want to make sure that you collect osteon population density data from consistent locations. All right, so I guess at the start, the biggest thing I would like you to take away from today is OPD. So OPD is essentially an acronym for osteon population density. And OPD really is a measure of how much cortical bone remodeling there is per given area of the bone. The area we normally measure in millimeters squared, and you can do it in microns squared. However else, again, if you're comparing things between different papers, ideally you'll be using the same type of measure. And here are just a few examples of publications that consider OPD in the research. It can be used to measure various different questions. Probably the most common is biomechanical adaptation. So how much bone is responding to mechanical stimuli in a localized area. But people have also used OPD in age of death estimation. So I briefly mentioned that last week We obviously didn't do it, but OPD is also actually used in those formulae for estimating how old someone is. Before we actually have a go at estimating osteon population densities, what we need to do is define what a secondary osteon is. And I think given that, you know, we have very little time and I'm trying to do it in a very concise way, the best way to describe, I guess, or define what a secondary osteon is that it's a product of cortical bone remodeling. I mentioned last week as well that it's essentially almost a self-sustaining unit of your cortical bone. So it forms a very important part of your bone physiology, or what we call bone remodeling. Remodeling is basically the metabolic activity of your skeletal tissue. And all it means is that under normal conditions, and when I say normal, I mean you're healthy, your body is in a, you know, homeostasis, nothing is really impacting it. What you experience is what we call the coupled or balanced process of bone formation and resorption. Now, most of you will know the resorption is done by osteoclasts, which are these huge cells that have several nuclei. They attach to bone surfaces, release ions, demineralize the bone tissue, and then basically absorb it. And then the formation is executed by what we call osteoblasts, so the cells that produce new bone matrix. So together, when they're traveling as teams of cells, as they travel through your cortex, they essentially become what we call a basic multicellular unit, a BMU. So in the literature, you would see a reference to that. And BMUs typically follow 5 phases. So research has shown that it's approximately 120 days to form one of those secondary osteons. Now remember, this is just an average, so it will vary from site to site, from a person to a person, but on average, that's an estimate. And so that BMU, basically for about 10 days, it gets activated, and then osteoclasts begin resorption. Then the cells actually start reversing, and so that's approximately 20 days. And then typically up to 90 days, what can happen is that the remodeling unit will continue formation of the bone, and then towards the end of this phase, we actually see resting. Now, to make it, I guess, even clearer, or I guess how to illustrate to you how bone remodeling can vary in different individuals, the best example to give is the amount of bone that gets remodeled in individuals. So what we typically discuss is, for adults, as you know, I mentioned that last week, our remodeling slows down massively, you know, when we're basically aging. And so approximately 10% of your bone is remodeled a year. Now, what we also mean by that is that the bone that's resorbed in one location of the bone is basically replaced by the exact same amount of bone in that same location. So you don't really see much different, it's just replacement. In children, in actively growing children, their remodeling is approximately 100% a year. What this basically means is if you have, you know, let's say like an 11-year-old, the bone tissue that you see in the skeleton in January is almost entirely replaced by new bone tissue in December. So it's just very, very, very rapid. Now, how does this all relate to what we're going to look at in the image itself? So here's a very nice diagram that I took actually from someone from Holland's thesis from 2012. I thought it was a nice drawing. If you think about a bone multicellular unit, it basically is a long structure. So you need to think of it as a 3D structure. And it's kind of like worms digging tunnels in your bones, which is not the nicest way to think about bone remodeling. But think about it that way, basically. Now, it looks a little bit different in trabecular bone, but we're not really covering it in the series. Trabecular bone is basically, you have cells that go on the surface of a trabeculae, and then they'll basically remove almost pancake-like, quite thin kind of packets of bone. Obviously, in the cortical bone, it's a tunnel. So it's a long structure that's resorbing the bone tissue. So you've got here, so imagine this is that bone multicellular unit. It's going through, it's digging through the cortical bone. So it's actually lined with osteoclasts. They're resorbing the bone. And then the kind of the middle of your BMU is basically lined with osteoblasts, which deposit osteoid. Now, once all of that is completed, you then see this beautiful completed osteon, which is what you then actually see in the thin section itself. So this was in about 5 minutes. I guess that's probably the most important thing for you to take away in such a short, session this morning. And that's why it's basically really valuable to us in biological anthropology and in any other really area that deals with skeletal biology and particularly bone histology. It's essentially a reflection of your bone remodeling activity. Now, John Skedros, who works at Utah, he is my absolute idol when it comes to bone histology and biomechanics. His publications are incredible. I can recommend those to you. So back in 2005, him and his colleagues wrote up this really interesting paper about biomechanics and histology and drew this really actually quite helpful diagram. So for today, what you really should remember, I guess, from this is that in order to calculate this osteon population density, the OPD value, what we need to be able to distinguish between in a thin section is what is a fragmentary osteon and what is, so I'm pointing one here, and what is an intact osteon. The reason why this is important is because as your bone is remodeling, the newer osteons, the newer BMUs are essentially replacing the older osteons that you had already built in your tissue. And so what you end up seeing are several different generations of osteons that either superimpose upon, one upon another, but sometimes they also simply just kind of try and squeeze in and fit in, in between the already existing osteons. And so altogether, that gives us a good idea about how well or how poorly, an area in the bone has actually remodeled. So when we calculate OPD, we simply add up the total of what we call intact osteons, which is NON, and that has to be divided by the section area, more on that in a second, plus the fragmentary osteons, which is what we abbreviate to as NONFG, and that gives us the OPD value. So before we actually move on to practicing that, could I get you guys to tell me how many intact osteons you see in this figure and how many fragmentary osteons do you see in this figure? If you could type in the chat option, just put for I for intact and give me the number, and then an F for fragmentary. Five. Yep, excellent. Yep. Okay, someone said 4 so it's 5 for intact, and then and 7 for fragmentary. Excellent. Okay, so you already, this is obviously not a real thin section, it's just a diagram, but you're already getting the gist of how we essentially look at what's intact and what's fragmentary. We cannot really always say that an intact osteon is actually the most recent one that formed. It's such a shame. It'd be great if we could do that, but we can really only do that experimentally. Because as you can imagine, remodeling can be localized. So you can have an area of bone that is never really, that hasn't really remodeled for ages, and then another one nearby that has been remodeling quite actively. All right, so that's that. Sorry, I'm going to try and change the slide. Okay. All right, so why is this important? Why look at OPD? So just give you a couple of examples, and then we'll move on to actually doing our own. You remember I mentioned the bone remodeling is a balanced process, but things can go out of balance. And it's literally what we would say, the remodeling is out of balance. And that a very, very classic example for that is osteoporosis. Osteoporotic bone, what happens is your bone remodeling is increased, but when we say that, what we actually mean is that bone resorption dominates over bone deposition. And so we then end up seeing in the histological section is something like this, where you've got basically just patches of bone completely basically resorbed. And as they increase in size and they spread throughout the thin section, they actually start completely creating almost, holes in the bone. And that's why you then see a fracture. So osteoporosis could be something you may be interested in for, in your research. But also biomechanics that I mentioned at the start. Bone microdamage and overload is something that, that I particularly myself have been interested in for my own research. And when we think about how bone remodeling responds in relation to biomechanical stimulus, we typically would use what we call a U-shaped curve of bone remodeling. So it's just this blue line here, this blue trace. Robling et al. In 2006 discussed this really nicely in this paper here. So if you have very little mechanical stimulus, what you typically see is, as I mentioned before, an increase in bone turnover, but it's actually the resorption, the osteoclast-mediated resorption that's higher than the bone deposition, which is what we see in osteoporotic bone. It's what you would also see if you go to space. So if you ever plan on going into space, please make sure that, you know, you do some exercise. And if the mechanical stimulus increases to the point where you're overloading your bones regularly, for example, if you're doing a lot of weightlifting that's pretty intense, such as weightlifting, basically, I think that's probably the best example. So anything that's weight bearing, but you're overstimulating your bone tissue, what your bone histology will show is something like this. You see here, it's a microcrack. And so this microcrack is what we refer to as micro damage. So it's not a big fracture, it's essentially a mini fracture in your histology. And that then needs to get remodeled away. And so you then see an increase in remodeling. That's that. And then just one more example, and then we'll move on. Malnutrition. Those of you who work in, I guess, in an area that deals with those sorts of questions, Payne and Brenton demonstrated in the 2006 paper, you've got it on the reading list, that severe malnutrition can actually also, I think they technically use the word arrest, that it can arrest remodeling. I'm not sure that's the correct term to use, I guess, to refer to that sort of thing. But here, when you look at the sample, it almost looks like it's from a young individual, which is what we looked at last week, you know, that you have a lot of primary bone and then just some isolated secondary osteons here and there. But this is actually a sample from an individual who's 45 years old. But it's actually an individual who had suffered from pellagra. So they were severely malnourished. So that could help you figure out, or I guess test your hypothesis if you have a hypothesis like that. Okay, so halfway through, which is great. So what we're going to do is actually have a go at estimating our own, well, not our own osteon population density, but practicing from the images that I supplied on my website. So those of you who want to do it right now, that would be great. What I will do is demonstrate what you should be doing. Feel free to make notes and then see if you can replicate that during the live session. If not, don't worry. Again, you know, this will be uploaded onto the website, so you can do it in your own time. And at your own pace, because it'll probably be a bit difficult, I guess, to follow exactly what I'm saying, but you may be fine. So I did ask for you guys to already have ImageJ opened on your screen and just download the two images. So what we're going to do is actually arrive at an OPD estimate, the actual data point that will be important to us, imagining that we're doing some interesting research question right now. So really what we've got to do is import the image into ImageJ, set the scale, count intact osteons, count fragmentary osteons, and then add them together and divide it by the image area, which I've here approximated 2 millimeters squared, but we'll have a look. All right, so I'm just going to stop this now. I need to show you my screen. Can you all see my screen? Is all good? I'm just gonna check chat. Yeah, okay, all good. So, okay, so we've got I'm gonna try and speak slowly so that you can follow, you know, everything that I'm showing with ImageJ. So you've got your ImageJ strip open with the tools. We're going to, let's start with maybe sample, I think I called it sample 1. This is the one that was scanned using polarized light. I am going to import it into ImageJ. I'm gonna pop it in there. It's gonna pop up on my screen this way. I'm just gonna move it around a bit so that I can actually see my tools. Okay, I'm actually making it a little bit smaller for you. There we go. Okay, first thing to do is to tell ImageJ how big the sample actually is. Remember, ImageJ doesn't really know what structures it's looking at, so you need to set the scale. If you go onto magnifying glass, click on that, zoom in onto the scale. So it's important, you can probably already tell that your images always have scale burned into the image. Click on the straight line tool, and then simply select the scale that is 200 microns. So we're just gonna do that. I'm probably not doing it very well right now because it's just a quick demonstration, but you get the gist. Analyze, set scale, and then tell ImageJ that the known distance is, we're gonna do it in millimeters, so it's 0.2 millimeters. Now, for today, we're gonna set it to global. because the other sample was taken at the same magnification and in a similar way. So so you can basically then just import the other image without changing the scale. Click OK. And then we zoom out again. You can zoom out using the minus key on your keyboard and then zoom in using the plus key. All right, now all we've got to do is look at the image and figure out how many intact osteons we've got. What we could do is actually, maybe so that you can see my screen. Okay, let me set up an Excel spreadsheet where I'll be writing down my values. Let's just do something like that. Okay. So I'll be noting my values in that so that you can see as I'm going through it. Now that we've set the scale, if you look in the corner of image J here, what you find is that it tells you that your picture is approximately 1.79 by 1.12 millimeters. So if you click M, it will actually give you the area of the image, or I guess, yeah, the area of the actual bone that you're looking at. So we know that it's approximately 2.003 millimeters squared. So if we just pop that in there, so our area is did I say 003? I think I did, didn't I? Yeah, that's right. All right, let's not save that. Okay, and then let's just count intact osteons. We can do it by clicking on the multi-point tool. So click on that, and then let's just look at them. Typically, I'll spend ages and ages doing this. I'll do intra-observer error test. I'll do an inter-observer error test to make sure that everyone's on the same page. As you can already imagine, you know, it's quite hard, I guess, if you haven't really done it before, because you're sort of just working with basic diagrams that show here's a perfect intact osteon, but then looking at stuff like at the actual picture of the sample, it can get a bit confusing. But so just for today, quickly, I would probably, let's start with the intact. So I would click on that one. That's probably intact. This looks intact to me. This one's possibly intact as well. I think this one looks like an intact osteon. All of this black stuff here, all of these patches of dirt, this is actually this is just bioerosion. It's just because it's an archaeological sample. So as you can see, that can actually also obscure some of the features in your thin section. So here, it's actually obscuring some of the Hevesian canals. The other thing I should also mention is that when you're writing up this, let's say for a publication, it would be very important for you to specify what the criteria of your image analysis actually were. So you could say, you know, you didn't count, did you count the osteons that were cut off by the image border? Here at the bottom of the picture, you can see there's an osteon here, one there and one there, but obviously we can't really tell whether they're intact or fragmented. So I, as a rule of thumb, actually exclude them. So I only really say, I really only counted or measured what I saw, you know, in that I could basically confidently identify, I should say. So I'll probably say this one looks intact as well. Okay, so for now, let's just stick to these. I think this is actually fragmented because there's a little bit going over there. All right, when you click M on when you press M on your keyboard, what you get is about 10. So I'm just gonna put for my intact osteons, I've got 10. And then let's just add up some of the more fragmented ones. What you can do is go on Image, Overlay, and Flatten. This will save, it will actually save those little dots that you've already added onto the image. So click No, we don't want to save that. And let's do the fragmented ones. So I think we've got, that one's definitely fragmented. This one looks like it's eaten away. This one looks like it's been remodeled here. This one looks modeled here. This one is a very good example here. You can see. This one looks like it's a little bit fragmented. I'm not sure about that one. Possibly this one. Not sure about these. Probably this one. Okay, so just let's click M. What do we get? Oh, sorry. It's actually added it onto, let me just do these and then do that. 11. So I've got about 11 of these. So for my NON of D, I've got 11. Okay, and so all we've got to now do is, so if we just sum these, that gives us about 21 intact and fragmented osteons. And then what we're going to do is just calculate OPD. So it's 21 divided by the section area. So my OPD value is approximately 10.48. Okay, and that's basically it. So I've got about 10.48 for this sample. And so this is the value that I would publish, or I guess I would add to my descriptives, or yeah, you know, when you're basically just discussing your results. Okay, so if you want to try and do this right now, we still have quite a lot of, well, not a lot, relatively a lot of time. You can feel free to do this right now if you want to. I will just go through the next section and I will redo it again, and feel free to, I guess, you know, write down your results and pop them into our chat option. Otherwise, just do it later if you have a bit more time. So I will now move this one in. It will ask you to disable global calibration, which you can just say, okay, it doesn't matter, really. I'm just gonna close this one down. All right, this one is transmitted light. So it's, you can probably tell that it's, I don't know whether for you it's easier or more difficult to distinguish between fragmentary or intact osteons. Personally, I prefer polarized light because you remember last week I was talking about how the light is actually distinguishing, it's showing very specifically individual lamellae, so it's a bit easier for me to figure it out. Sometimes with transmitted light, it's quite easy as well though, because you can then really nicely point out cement lines of the secondary osteons. More on that next week. Okay, so we know that the area simply is almost the same. I'm just gonna click on these. I don't know if you guys are practicing right now, but if you are, good luck. This one you can tell straight away that it's actually not as remodeled. They look like they're just very tightly packed. I think this one's going over that one. This one looks like it's remodeling. This one's quite small. Yep. So that's basically what most histomorphometrists would do. You just sit in front of the screen. That's probably a small secondary osteon. These ones are connected. This is a Volkmann's canal here, everyone, that one. And there's one here as well. I can't tell about, okay, so what we've got for this one. Sorry, I keep leaving the old. Okay, so for this one, I've got a bit more. I've got 17. So area is the same. We've got 17 intact. And then we should have fewer remodeled ones. And let's just find a couple of remodeled. These all look like they've been remodeled. But yeah, so sorry, what I was saying, yeah, so we'll just, most bone histomorphometrists, I should say, will just sit in front of the screen and do this for hours and days and months on end. So it is, if you're working with fresh bone, it's probably a little bit easier because you can automate the process quite a lot. Some researchers, there's a bunch of people in the US who have been applying geographic information systems to mapping secondary osteon population densities. That works really well if you're working with very, very fresh, nicely preserved bone. For a lot of us working in forensic or archaeological contexts, as you can imagine, the bone is actually obscured by you know, post-mortem processes. So it's not that easy. But so you actually have to manually sit there and pick out and, you know, and identify what is it that you're looking at in your thin section. But this is personally what I find really appealing about it. I love monotonous type of work, and you know, I actually really quite enjoy image analysis. Anyway, sorry, I feel like I'm talking too much. So I probably missed this one. Anyway, so just for now, let's have a look at what we've got. I keep forgetting to close this one. Okay, so we've got 8 fragmented. And again, let's just have a look at this. So our OPD is 25. And so that I should be able to move that here, I think. Okay, so my OPD for that one is 1248. Yep, that's right. Okay, and that's about it basically. So what we figured out is that this image, the sample, so that was actually sample 1, not sample 2, sample 1, even though it's got fewer remodeled osteons, I mean, that's what it looks like anyway. Yeah, it's the OPD value is a little bit higher. So if you repeated this on in your research, you know, case study or whatever, or your research project, if you've got lots and lots of samples from different individuals and you've consistently looked at the exact same area, you could start seeing some variation in OPD, which will then give you an insight into the remodeling that's localized in that individual. Have a think about your research questions, I guess, or just generally your ideas, and then we can talk about them at the end of the series. I mentioned in my first email that we'll set up a whole other session for after session 5, excuse me, and we can have a chat about that. So I work with some people who work in the jaw biomechanics area, for example, so they're often interested in just sampling some locations in the mandible, and then linking that to the use of of the jaw in chewing and eating. Yeah, so the world is your oyster, basically. Let's have a look at some of your chats that are coming through. There are some questions I'm not sure I can actually, we're gonna have to leave in a okay, yeah, I can put some labeled. Okay, yeah, that's fine. Yeah, someone's asked, do you have some images where the NON and NONFG are labeled so we can compare? Yeah, sure, I'll do that. I'll put that up online. Maybe I'm missing, but if osteons pair, do we need to divide everything? Yeah, that's a good question. So you can divide both the NON, and so basically no matter what you do, you still get the same value. If you just take the intact osteons and divide that value by the image area, that will give you basically a density of intact osteons only. If you do the same thing for the fragmentary ones, again, you only get a density of the fragmentary osteons. When you sum them, you then get your overall OPD. It's usually the OPD that most researchers are interested in. So when you're actually, when someone's peer reviewing your paper and you only report fragmentary osteons, you need to have a really good reason for that. You may say, I'm really only interested in the fragmented osteons. But you should typically basically report the OPD. If you look at most of the publications like I've done, I would actually report everything. So I'll have intact, and then the fragmentary, and then the OPD value. Yeah, that way we're kind of transparently reporting everything, basically. Okay, I think that's about it for today. I hope you managed to play around with your images. If not, hopefully you can do it at home. Excuse me, my voice is going already. And next week we will take a look at, actually, I need to stop this one and then go back to the presentation. Okay, we've got about 1 minute. Okay, so next week we're going to do a similar thing, but we're going to move into looking at the geometric properties of the secondary osteons and how that relates to your research question. So we'll take a look at Haversian canals, and then tracing secondary osteon cement lines. And here's just a list of references. And I can see a few more questions coming in, so I will download them, save them, and then post them on the website under session 2. That's it for today, everyone. Thanks so much for logging on again. See you next week.
Thank you.